Welcome to clickmyproject.com. Title of our product is a dual series resonant DC to DC converter. Abstract of our product is a dual series resonant DC to DC converter with zero voltage switching and zero current switching feature is proposed in this process. The topology consists of the two switches and a clamping capacitor on the primary side of the isolated transformer. The two switches are operated in complementary mode under the pulse width modulation input signal from the controller of pulse width modulation. The secondary side of the transformer is connected to the load through the two series resonant circuits and a half-bridge diode rectifying stage, in which the rise and fall slope of the diode currents are limited by the slope of the currents in the resonant circuit, resulting in reduced switching losses in the diodes. The two series resonant circuits provide the power transfer to the output load without interruption through the positive and negative cycle operation in our process. It is shown on this output voltage of the proposed converter can be regulated by using the pulse width modulation control or frequency modulation control. They are used as a controller of our process. Both step down and step up voltage conversion can be achieved using the proposed technology of the zero voltage switching and zero current switching feature DC to DC conversion dual series resonant. Now we are going to discuss about the flow diagram of our product. In our product, flow can be implemented using the two different switches. They are made up of the MOSFET devices or IGBT diode. The input signal of our process is DC voltage. The input DC voltage is directly applied into the switch 2 and clamping capacitor. This clamping capacitor used to consider the zero voltage crossing and zero current switching operation. This output of the switch 1 and switch 2 can be directly applied into the transformer. This transformer can be single primary and dual secondary operation. This transmitter or transformer output can be directly applied into the half-bridge rectifier. Half-bridge rectifier similarly implemented using the two different diodes and the some reference inductance for our rectifying process. Next, this half-bridge rectifier output can be directly applied into the final load of the resistance and capacitance. This load resonant of resistance and capacitance can be used to monitor the final output waveform of our process. This switch 1 and switch 2 can be run based on the controller signal. In our process, the pulse width modulation can be act as a controller of the process. The output from the pulse width modulation can be divided into two paths of pulse waveform. They can be used for the mux operation. Dmux to split the two input signal from the pulse width modulation. They can be applied directly into the switch 1 and switch 2. They can be produced the output of the waveform of control design. They are directly applied into the transformer. This transformer can be applied to the directly proportional to the half bridge rectifier, and then finally the output can be calculated using the load resonant of capacitance and resistance value connected in parallelly. Now we are going to discuss about the running procedure of our product. In our product can be used in implemented by using the MATLAB or 2013 version. The 2013 version of MATLAB tool can contain the Simulink library. Our process can be fully implemented using a model file. The model file can be fully implemented using this Simulink library. Open the tool window of MATLAB 2013. After open the tool window, you can create this page. In our process, we can use this path window to select our process coding path, copy the model path and paste it to this path file. After completed the path, your file name can be assigned in this left hand side. After completed, we can select the Simulink library to open the block of the model file. In this process, we are named our product design for 3-phase VSI. VSI in the sense voltage source. This design controller can be implemented in the subsystem process. This gray color box is on a subsystem. Double click to open the subsystem. This is the controller design of our product. The scope will be used to finalize the final waveform of the controller system. Double click to open the scope window to view the final output waveform. Fit to screen to fit the screen into the final output waveform. Expand this waveform. In order to first waveform is inversely proportional to the second. If the first waveform will be 0, the second waveform will be directly proportional. So the second waveform will be the 1. Similar process can be obtained in this pulse width modulation control. These two waveforms can be directly applied into the 3-phase VLSI application. In this VSI application, final output can be monitored in this final scope, and then further implemented transformer output can be implemented in this scope. Double click to open the scope window. Apply fit to screen in this waveform. This is a middle waveform of the transformer. Obtain the final output waveform using this final scope. Double click to open the final scope. This is the output waveform of final scope. Scope the fit to screen. Apply the auto scale to fit to screen the final output waveform. They are the final output waveform of our product. Thank you for watching this video.